Hey guys, it's ZF Productions here, and today I have finally done it. After so long, it's finally complete. So this, if you don't know, is a recreation of the Clawshot from The Legend of Zelda Twilight Princess. I took a lot of time making sure the measurements, the weight, the mechanisms, every single detail is exactly as it should be. And today, I'm going to be testing it right here for you. So I'm really excited. I've actually not tested it before. So I have a target on the other side, but I'm by myself so I can't show everything. But this is going to be really cool, alright? I'll see if I can try and get a different angle later, but this is going to be cool, alright? Alright, let's get in a good stance. Alright. I'm so excited for this. Alright. Oh! Oh! The Clawshot, Twilight Princess's version of another beloved Zelda item, the hookshot. With this item, one is able to pull objects towards them, but most notably, pull themselves to any surface the claw can latch onto with high speeds. This poor fella had the smarts to make such an item, but not the wit to think whether or not he should have. Now, there's not much doubt that the Clawshot would be very dangerous in real life, but would it be enough to rip off your arm? To find the answer, we need to go back to Newton's second law. F equals ma, or force equals mass times acceleration. In order to find our answer of how much force the Clawshot will put on your arm and body, we need to figure out the mass of Twilight Princess Link and the Clawshot, as well as the acceleration it travels at. Let's hope we can find all this information on YouTube, but I'm positive it will, especially like the mass and also potentially we might need the height of it. So if we can manage to find all that, then we can start working out this, and then we can move on from there. So I'll see you guys when I manage to do that. Yeah, so mistakes were made. First thing is, like I said, mass of Link and the Clawshot. Well, where do we start with that? We need to find Link's height in Twilight Princess. Then we can compare them to everything else and get our heights and our measurements and all that. So then, what is TP Link's height? Well, see, now that's a little bit of a slippery slope, but don't worry. Luckily, Ganondorf is the same between Ocarina of Time and Twilight Princess, or at least he should be around the same height, right? So, in Hyrule Historia, they actually list his canon height, and luckily for me, being the nerd I am, I have Hyrule Historia. So let's turn to that and let's find his height. Oh yeah, let's see, about 7'7". All right, and then you do the math and you compare that to Link, and that comes out to like that's not right. And that doesn't really make any sense, considering that Link's actually one of the taller people in Twilight Princess. Like, sure, he's short compared to Zelda, and he's short, and he's not like the tallest, but 4 foot? That doesn't seem right at all. So we're gonna have to turn to another aspect of Ocarina of Time that's not in the books. Alright, so heading into Ocarina of Time, if you go to the lab, you can actually sink down with the iron boots and get a measurement of Link's height. Now looking at this, we get two values, anywhere from 5'4" to 5'7", and then taking that into account and measuring Ganondorf, you get about 9'9", which actually puts Twilight Princess Link around the same height as Ocarina of Time Link. Now, in order to stay fair to the prior measurement, I'm going to go ahead and go with the lowest value of 5'4", and that is what we're going to deal with for Link's height. Okay, sweet, we got it, right? 5'4". That is Twilight Princess Link's height. Perfect, done. If we actually compare him to the height of the Clawshot itself, we actually get the height of it to be about 2 feet. That's all good. Now we got this. But what does Link weigh? We need that for the mass calculation. Well, thinking about it, if you go to a BMI chart, it puts an average healthy person that is 5'4" at about 143 pounds. Now I'm gonna add about 10 pounds to that just to account for all the feats that he's shown doing in the games. He's shown throwing Gorons around with just brute strength. He's shown to be able to wrestle goats with no extra power-ups or items. And Link would have to be somewhat close to that weight of a farming goat in order for him to be able to wrestle it. Now, order-eating goats don't exactly exist in real life, but if we take the weight of a real-life farming goat, it puts it anywhere from 170 pounds up to 300 pounds. How do we get the mass of the Clawshot. Well, that is a lot more complicated. If we want to find how heavy the Clawshot is, we need to first find how long it can shoot. Because we need to calculate how much chain this is holding, which adds to the weight overall.
Alright, so in order to find how many chain links are in the Clawshot itself, or the whole chain, I actually had to go to the Skyview Temple and hang down as far as the Clawshot would allow me to, which in turn would mean its max length. So I went ahead and did this, trying my best to count it as accurately as possible, which it's hard given that it's only like 3 pixels, but when I did, I got an average of 157 chain links after counting them 3 times.
If we calculate each chain link, it's about 3 inches, and it is 2 inches wide. Now we gotta consider how thick it is. Now, I've calculated that to be about 1 centimeter. And the reason we need the thickness is because, remember, these chains are overlapping. So if we want a real measurement of how long these are, we need to take off about 2 centimeters for both times the chain overlaps. See, overlaps once and then twice right here. Subtract 2 centimeters and then multiply that by 157. And the final result we get, 116 meters. Now, the reason I have it in meters is just because to make it much easier for us, because meters is just a lot easier. But anyways, we're getting ahead ourselves because we didn't actually even need this yet, so let's just put this value in the back of our minds. Now, going back to our chains, how exactly are we going to calculate how much these weigh? We don't even know what material they're made out of. Well, I was reading around, and on MatPat's video, one user suggested that beryllium might be a good substitute for steel because it has all the qualities of steel, but not nearly the density. And that's what I'm going to be using just to give this as fair of a shot as anything. So, we need to find, in order to find its mass, we need to find the density and the volume. We have the density of beryllium already. Now we just need to find the volume. Now, luckily for us, these are basically squares. So, all we need to do is just multiply 3 times 2 times 1. Now, for the sake of simplicity, I'm going to be turning all of this into meters because we need to stay consistent. I've just been using inches because that's just easier for the measurements. But converting all of this into meters, now the second square, which we're going to subtract from, because keep in mind, these chains have a hole in the middle of them. So, then that gives us 0.752 by 0.498, and then it's still 0.01 meters. And that gives us, and all we have to do is just subtract what we get by multiplying this volume by the density. So the density of beryllium is actually 1,850 kilograms cubed. Now that we have this, all we need to do is multiply it by our 2 values and subtract them. Easy. We get the final 1 chain link, so 1 chain link equals 0.58386 kilograms. Sweet, now we got this. All we had to do is multiply it by 157 because there's 157 chain links, and that gives us a final mass of the chain alone to be around 9.2 kilograms. Or, in layman's terms, around 20 pounds in the chain alone. So now we need to find the rest of the mass for the Clawshot. So we have the chain, now let's focus on this middle section. If you look at it, it can roughly translate into a cylinder, in which we only need to find the height and the radius. So I measured it and I got the height to be about 0.1778 meters and the radius to be 0.062 meters. Now if we put that into the equation for volume of a cylinder, which is pi r squared times height, we would get the volume. But then remember, this is hollow, so accounting for about maybe, I don't know, 3 millimeters of wall space, and then we have to add the middle cylinder because the chain needs something to wrap around, we would get a final mass of 0.580 kilograms. And if we were to add that back to the mass we already got for the chain, we would get roughly 21 pounds. Now, in the sake of time, interest, and just, thinking about it, I'm going to say that the whole Clawshot together is roughly 30 pounds. The reason why is you have to consider the way Link is holding it. He's holding this object up with one hand and basically controlling most of it with the arm/wrist. The max it could be is anywhere from 30 to 40 pounds in order for a regular human to be able to do it reasonably. And we're going for reasonably here. So I'm going to put the final mass at 30 pounds, which allows us to go and finally work out the rest of the math. Alright, so now that we have the mass worked out, now we need to find how fast is the Clawshot pulling Link and how fast is it going? How fast is it accelerating? We'll go over all of that. So, velocity, which is speed, equals distance over time. So we have how the farthest it can go, which is 116 meters. Now I timed it in-game, and I got the time to be 0.83 seconds for T. Now, if we divide these by each other, we get roughly 201 meters per second. Yeah. That's fast. Very fast. But we also have to consider Link is going from 0 meters per second squared to this in a fraction of a second. In about this much time. So, thinking about it, if this is how fast it can extend, this is how fast it retracts, because the velocity in-game is consistent. In order to solve for the acceleration, I plugged all the values that we've gotten so far into the kinematic equations. The kinematic equations are basically a set of equations that help us determine acceleration and various other things. You'll learn about that later. Either way, it's a very good tool for me to work backwards in order to find acceleration. Plugging those in, I was able to get a range of acceleration anywhere from 84.5 meters per second squared all the way up to 173.65 meters per second squared. That's a lot, but exactly what we need. So, let's go back to what I said at the beginning of this video. Force equals mass times acceleration. Well, we just worked out the mass, and we've just got the acceleration. So now let's put them together. Alright, now we're at the final stretch. All we have to do is just put everything we just did all together. So as we said before, Newton's second law, force equals mass times acceleration. Well, we got the mass of Link to be about 69.3, or 0.4 if you round, and then 13.6 kilograms, roughly. These are the larger values, for the Clawshot in total. Combine those together and we get 83 kilograms around, and then all we had to do is just multiply that by the 84.5 all the way up to 173.65 meters per second squared we got for our acceleration of Link and the Clawshot. And we get our final two force values of anywhere from 14,414 newtons all the way up to 28,073 newtons. In MadPat's video, he actually said that it would only take about 30,000 newtons of force to rip off an arm. I've looked up other sources, and others say that it would take much more, others say it would only take about 10,000. But either way, if we use MadPat's value, just because I'm pretty sure he put a lot more research and thought into it than I did, we can say that if he said that 30,000 newtons is enough to cleanly rip off an arm, 28,000 newtons should be enough to rip off your arm, just not cleanly. The physics of The Legend of Zelda Twilight Princess Clawshot in real life. Will it rip your arm off? Probably. If not, it's going to break a ton of bones, probably rip your shoulder out of its socket, and probably most of the way off, at the very least. So, what have we learned? Don't try and make this in real life. Now, if you excuse me, I gotta take my friend to the hospital.